Hello guys, welcome to Self-Help Maths Academy. So today I'm going to discuss about some more examples on the binary operations and then the identity element with respect to a binary operation and the inverse and so on. Let's see. Let's begin. So let me take this example first. Say it asks for show that the relation say dot the binary relation which is given by a dot b is equal to a to the power b on the set of all natural numbers, where for all AB belongs to N. So is it this operation is associative? That's what we need to check. Is it associative? So let's see. How do we tackle this example whenever the questions on associative will be asked? So what is the given operation which is defined? And obviously it is defined on the natural number set. So if I consider if A, B belongs to N, the defined operation is A dot B is equal to A to the power B. So hence the operation is A dot B will be equal to E to the power B. Okay, so it's an operation on the set of all natural numbers. Now in order to prove the associativity, we have to prove A dot B dot C should be equal to A dot B dot C. So now let me take this part. If I consider A dot B dot C, A dot B dot C will be equal to, I write this A dot as it is, B dot C. If I take the binary operation here, it is the first element to the power second element. So like this, the first element here is B to the power second element, that is B to the power C. As we know, A dot B will be equal to A to the power B. So this is equal to now, again, here this is the first element and this is the second element. So first element to the power second element, that is second element is this one. So this is now A to the power B to the power C. Let me take this as star. Similarly, I will take on the other hand A dot B dot C. Say A dot B dot C. This is equal to, we know what is A dot B, that is A to the power B. So dot C. Now this is our first element and this is our second element. So we know that A dot B to the dot C will be A, this I'm writing as it, the first element to the power second element. So we know there is a like the identity, we know that by the indices rule, say A to the power M to the power N is equal to A to the power M into N. So here this is different, it is A to the power M to the power N. So this is different and this is different. So now let's see this. If I write, this will be A to the power B into C. Okay, so this, let me take it as double star. So if I observe star and double star, both are not equal, hence A dot B dot C is not equal to A dot B dot C. Hence it is not associative. Therefore the given operation is not associative. That's how we're supposed to try, go for the problems. Okay, so let's see another example where simple examples I'm considering so that the concept will be more clear. Let's see. For example, show that the multiplication, the ordinary multiplication, the multiplication, this multiplication is a binary operation. It is the binary operation on the given set A equal to 1 minus 1, but not on the set B equal to say 1 comma 2. So here the question is, we need to check whether it is a binary operation the ordinary multiplication is a binary operation in this set or not, but it is not the binary operation on this set. That's what we need to check. Let's see, how do we check it? So let me consider the first set. In the given set, the set I take, say, A, which is equal to 1 minus 1. Okay, so we find that if I take any element of this set, for example, I'm taking 1 and also I'm multiplying with 1, I'm getting 1. This is equal to, this is again belongs to A. If I take the element 1, I'm multiplying that element with negative 1. So this will be again negative 1. So this is nothing but, again it is belongs to A because it is the element of A. Now I'm considering negative 1 into negative 1. So which is again 1. This is belongs to A. Similarly, I take negative 1 then into 1, which is again negative 1, which is belongs to A. So all the possible combinations I have checked for. Hence, after multiplication of each element, again it belongs to the given set A. Thus, the multiplication, ordinary multiplication, is the binary operation on the given set A. So let us check it for B now. Similarly, we will check it for B. Okay, let's see. The given set B is 1 comma 2. So when I check for a B, let's see if I take 1 with 1. This is 1 which is belongs to B. I take 1 and I take the element of 2. So which is 2 again belongs to B. Now I'll take element 2 and 1. It is 2 which is again belongs to B. Let me take 2 and also 2 which is 4. This does not belongs to B. You can see there is no 4 here. So hence it failed at this particular moment. Hence the ordinary multiplication will not become a binary operation on this set. It won't become a binary operation, whereas it become a binary operation on this set. Okay, so like this we can tackle the examples. Let's see another example. This says prove that we have to prove now, prove that, say, the dot operation is neither commutative neither commutative nor associative. Okay, nor associative on the set of R, okay, of a real number which is defined as A dot B equal to A plus B plus A square B. This is true for all AB belongs to R. Okay, so let's see this example. How do we solve this, and how do we actually approach this example? So they're asking you, they have defined the binary operation this way. They ask us to check whether they're I mean like we have to prove that it's neither commutative nor associative. So let's see what is given. Given A dot B will be equal to A plus B plus A square B. This is true for all AB belongs to R. Okay. So now in order to prove the commutative, I have here A dot B. I just have to check for B dot A. So if I take B dot A, the defined binary operation is the first element plus the second element plus the first element square into the second element. So if I take that, this is first element plus the second element, first element the square into the second element. So if I take this as say star and this as say double star, you can see, observe, both are not one another same. Hence A dot B is not equal to B dot A. Hence we can say that the binary operation is not commutative here, is not commutative. this is not commutative. So in order to check for the associative, now let's see, we need again for associative, we want to check A dot B dot C equal to A dot B dot C. So here you need to check the left hand side and the right hand side, guys. So once they're equal, they're associative. If not, then we are not, uh, we're concluding that it is not associative. Let's see. Now let me take A dot B dot C, which is equal to, I'll write A dot as it is. So let's use the binary operation B dot C, the first element plus the second element plus the first element square into the second element. Okay, this is equal to, now this is your first element and this is your second element, if I consider that way. So then this will be A first element plus the second element. This is second element you write completely, plus the first element square into the second element. Yeah. Okay, so if you just see this one, let me take this as say 1. Similarly, I'll go for A dot B dot C, which is equal to, now A dot B we know, which is defined as A plus B plus A square B, and this is dot C as it is. Now again use the binary operation, that is equal to the first element, that is A plus B plus A square B, plus the second element plus the first element square, is A plus B plus A square B square into second element. Okay, if I just have this one, you can take this as a second element. Obviously you can observe this is just A square into this element, whereas this is square into this element, whereas this is only the left, this part here you can see this is also we have different. So hence from 1 and 2 it is clear, 1 and 2 it is clear that A dot B dot C is not equal to A dot B dot C, hence it is not associative, hence dot is not associative, it is not associative. So this is how you'll be concluding the examples when it is related to the binary operations. So now let me see, we will now define the, the identity element for the binary operation, which is very important, and with respect to the binary operation, and even the inverse element will be defining. So let's see the identity element. How do we define the identity element here? Okay, so basically the identity element for the binary operation, when we're defining, it is said to, like, we're going to define now two types of identity element, that is left identity element and the right identity element. So usually, in case of the like numbers, how do we do it? If suppose I have any number, say A, and if I add that number, I'll get back the same number. That's how we actually do it in the addition case. So in case of multiplication, it is that number after multiplying, I should get back the same number. That means here 0 is the identity element with respect to addition, and 1 is the identity element with respect to the multiplication. So this is our usual addition and multiplication. Now when we are talking about binary operation, so it should be in such a way that if I take dot as my binary operation, okay, and let me take any element, say A belongs to the given set A, okay, such that if I take an identity element, I am talking about here left and right both first. So if I take a left identity element, so EL, I denote it by dot A should give me A. This should be true for all A belongs to A. Similarly, this is your left identity element. Similarly, for the right identity element, I take the given any element A belongs to A. If I multiply, I mean, if I do the binary operation with this, from right-handedly, I'll get the original element. That is, this is true again for all A belongs to A. If that is the case, we call EL as the left identity element, ER as the right identity element. Okay. So if there is now, if this is the case, if this EL is equal to ER, this is equal to, if we generally denote it by E, then E is called, two-sided identity, or simply we call it as identity element. It is called identity element. Okay, which is related to the operation dot which is given. Okay, so we can also write it as A dot E equal to E dot A equal to A. So it's the basic understanding is whenever you have a binary operation and when you take a element and then you do the binary operation with the element, if you're getting back the original element, then that element we call it as the identity element. Okay, so let's see now the inverse. How do we define the inverse of the binary operation? So inverse element. Again, if dot is the binary operation, okay, defined over the set A, and let E belongs to A be the identity element now for the operation A. Okay, now because in order to define the inverse element, we need the identity element. Then say two elements A comma B belongs to A are said to have the inverse element with respect to E. Okay, if I take the binary operation A dot B, or I take it as B dot A, if I'm getting the identity element, then I call B as the inverse of A. B as the inverse of A. Okay. So if A dot B is equal to E, for example, if I just have this A dot B equal to E, then I call the A is called as the left inverse of the B. And if I have B dot A equal to E, then I call A as the right inverse of the element of B. Okay, so basic understanding, the quick understanding of the inverses, whenever you have two elements in the given set, then if I'm doing the binary operation with those two, and then I'm getting the identity element, then I call one of the element as the inverse of the other element. Okay, so that's the simple understanding of the inverse and the identity element. Now let's see some examples on this. How do we actually identify the inverse element and the identity element in case of the binary operation? So let's see one example. So I'm defining a binary operation. Okay, I may take also star. Let me take star as a binary operation on the given set R. Okay, so it is defined as A dot B equal to A plus B minus 3. This is true for all AB belongs to R. Now we have to find out the identity element. We need to find the identity element, that is E, and we have to find out the inverse. What is the inverse? That's the question. So this is the defined binary operation. So let's see how do we tackle with these examples. So what is given first we will write. Given that A dot B is equal to A plus B minus 3, and this binary operation is defined on the real number set. This is valid for all AB belongs to R. Okay. Now if I consider, in order to find out the identity element, I consider let E be the identity element, it is the identity element for the operation dot. Okay, let me take that one. When I say operation, it's a binary operation dot. Okay, then as per the definition of a like identity element, for any given element A, if I do the binary operation, I should get A. This is valid for all A belongs to R. Okay. So now by using the definition of an identity element, let's see. Uh, but it is defined that A dot B is equal to A plus B minus 3. So in place of B, I have E here. So let's apply the binary operation. So it is A plus the second element is E minus 3 is equal to A. So by the left cancellation law, by the cancellation law, we can do this. So what is E will be equal to? E minus 3 is equal to 0. So simply E is equal to 3. E is equal to 3. So therefore E is equal to 3 is the identity element. This is your identity element. This is our identity element. Okay. Now let's see. They also ask us to find out the inverse element. Again, now we will take again let B be the inverse element. Inverse element. Okay, when it has the inverse element of A, okay, then we must have A dot B equal to E. This is equal to B dot A. So this is by the definition of inverse element where E is the identity element. Okay, so now let me consider A dot B equal to E. So when it is A dot B equal to E, then it is just simply by the definition A plus B minus 3 is equal to E. But by the previous, we have know that what is E value. E value is equal to 3. So substitute 3 here. So A plus B minus 3 equal to 3. So I've got the value of E as 3. Now simplify this. It is A plus B will be equal to 3 plus 3. So therefore A plus B is equal to 6. Now B is our inverse point. So let me take this A on the other hand. So B will be equal to 6 minus A. So hence B equal to 6 minus A is the inverse of A. So this is the inverse element, and we have got identity element E is equal to 3. So this is how we are supposed to find out the inverse element and the identity element of a given problem. Okay, so another problem, let me take for the inverse and the another example I'm taking now to solve the inverse and the identity element, and if it exists. Okay, sometimes not necessary that for all the binary operation it exists, the inverse in particular. Now for example, on the set of a real number, a binary operation dot, which is defined as A dot B equal to A plus B plus A square B. So this is true for all AB belongs to R. So they ask us to find out what is the identity element A, and also we have to find out the inverse if exists. Okay, if exists. So we need to find out the inverse on this particular example. So let's see what is given to us. Given A dot B equal to A plus B plus A square B. This is true for all AB belongs to R. Now we have to find out the identity element, and also we have to find out the inverse element. So let's see that I consider now let E be the identity element. We have taken let E be the identity element. So by the definition of identity element, we know A dot E should be equal to A. This is valid for all A belongs to R. So now we have to just check A dot E is there. So we have got the binary operation. If I apply this, it is A plus B plus A square B is equal to A dot B. This is what we define. Now I'm going to apply this. So here it is A plus E plus A square E is equal to A. Now I can cancel this a and a. I'm left with e plus a square e equal to 0. I can take e out. This is 1 plus a square is equal to 0. So here you can observe clearly, for any positive real number or a negative real number, the square will be always positive. And when I take a positive number and I add with a 1, I'll get still positive. So that means this will be always positive. This cannot be 0. So this 1 plus a square cannot be 0. Hence what has to be 0 now? E should be equal to 0. So therefore E equal to 0 will be the identity element for this given binary operation. Now let's see the similar way. We're going to find out the inverse element for this. So hence what I take is, now I'm going to deal with the left inverse and the right inverse separately. So let's see how do we actually go for the left and the right inverse. Now again, let B be the, I consider B be the, say, right inverse. It is the right inverse of A. Then we must have A dot B equal to E, where E is the identity element, where E is the identity element. So when I have A dot B equal to E, so by the operation it is just A plus B plus A square B equal to, say, E. So whenever we have this operation, we need to check this. And now we know that what is our E value by the previous, it is 0. So hence this will become A plus B plus A square B equal to 0. Okay, so here what I can do is, since this will be the case, I can take this A out on the other hand because I want B. So B plus A square B will be equal to negative A. So in this two I can take B out. So I left with 1 plus A square, which is equal to negative A. So I want B. So dividing both the side by 1 plus A square, I'll get B is equal to minus A upon 1 plus A square. Let me take this as some start. So this is our right inverse now. B is equal to minus A by, let me highlight this. This is our right inverse. This is our identity element. Now let's see. I'm going to consider the left inverse now. Also, if you see the dot operation as A dot B is equal to A plus B plus A square B is there. And if I take B dot A, this will be B plus A plus B square A. So this implies this is not commutative. I mean, this given operation dot is not commutative. So therefore, I just can't write, I mean, like, by using A dot B equal to B dot A, which is equal to E. We can't take that way. That's the reason I have to find out now the right inverse separately. So since it is not commutative, the dot operation is not commutative. Now let's see the left inverse of this. Let C be the left inverse. Let C be the left inverse of A. Then C dot A is equal to E. So this will give us first element plus the second element plus C square A equal to E. Okay, since E will be equal to 0. So as we have find out the identity element that is equal to 0, this implies C plus A plus C square A, which is equal to 0. Okay, so now what happens here, we can take this C, if you just take this element again in this way, say for example C square A plus A or plus C plus A equal to 0. So here if you observe carefully, it is a the quadratic equation with the variable as, say, for example, if you take it as c, and then now what we do is, if I consider this as, for example, you just take this as x square a plus x bx plus c equal to 0. If this is the quadratic equation you have, then you know your x will be equal to minus b plus or minus square root of b square minus 4ac upon 2a. Okay, so hence I use this one in order to calculate this. So here what I get, this will give me c will be equal to minus b, that is minus 1 here, so the b value is minus 1, plus or minus square root of b square, that is 1, minus b 4ac, that is 4, a is a, c is also a, divided by 2a. So where, which is the real value? This is real only when your 4a square must be less than or equal to 1. This implies your a square must be less than or equal to 1 by 4, and a should be less than or equal to 1 by 2. If this is the case, then this will be real. Else, it is complex, and also this one will not be existed when your a is equal to 0. If a is equal to 0, then anything divided by 0 will be, it does not exist. I mean, it is like infinity. Hence in these two cases, this root is not real. So therefore, if you, thus we find the left and the right inverse of the a which are not equal. If you see there, this is your left inverse, and here we have found the right inverse. This is your right inverse, so both are not one another same. Hence we find that hence we find that the left inverse and the right inverse are not equal, are not equal. Thus the inverse does not exist. Inverse does not exist. Okay, so like this we can take up some examples. I'll just give you for your work, so you just try them out. For example, if I have defined the binary operation on the given set Q as, say, x star y is equal to xy by 3. So you just find out the identity element E and find the inverse element on the given operation. On the set of rational number, the binary operation is defined this way. Find the identity element and the inverse element, and comment it in the box. The answer will get back to you. Okay, with this, let's conclude the discussion. In the next discussion, we'll come up with the next topic. Till then, take care, guys. See you all in the next video.